Okay, so we've been talking chapter 9. We talked about in chapter 9 here intermolecular forces mainly. We talked about intramolecular forces, but we also talked about intermolecular forces. A reminder that intramolecular forces are the forces within a molecule. So again, that would be something like covalent bonding, ionic bonding. So for example, the bonds here within one molecule is an intramolecular force. We talked mainly about intermolecular forces, which are the forces that hold multiple molecules together. So like two water molecules are held together through intermolecular forces. There's several sort of groups of intermolecular forces we talked about. Sort of the strongest is hydrogen bonding. And that is a bond between hydrogen and some electronegative atom like nitrogen, oxygen, or fluorine. All intermolecular forces are pretty much the positive negative attraction that holds those together. So there's like a positive side and negative side to a molecule, and that's essentially what holds it together. Dipole is the next sort of strongest, and really hydrogen bonding is a type of dipole interaction. And dipole interaction are really the main sort of force that happens between sort of polar molecules and polar molecules. And these would be polar molecules that lack the ability, the hydrogen bond. The hydrogen bonding is sort of the one that's also between polar and polar molecules, essentially the main sort of force that holds those together. The difference is, though, it has the ability to hydrogen bond, obviously. And sort of the weakest out of all of those sort of intermolecular forces we talked about are what are referred to as dispersion forces. And these are these temporary sort of forces that create temporary dipoles, you know, that's sort of a positive negative side where there can be interaction, but they're really not permanent. And it can be a result of a instantaneous dipole where all the electrons sort of go to one side of the molecule versus the other and creates a temporary sort of separation of charge. You could also induce this type of dipole by putting something that's, you know, has a charge like an ion or something that is polar, which will temporarily sort of move the electrons in the nonpolar molecule and give it a way to interact. But for the most part, dispersion forces are really the main sort of force used by nonpolar and nonpolar molecules as to how they interact. For the most part, everybody can do some type of dispersion forces, so even polar molecules can do some dispersion forces, which is why they're able to sort of interact for a while with nonpolar things. But the main difference, obviously, is in the dispersion force situation, you really don't have a fixed dipole moment in a molecule, as opposed to dipole, where it is always fixed, it's ready to go, it's ready to have that interaction. It doesn't need anything to happen for it to do that because it's a polar molecule, so there's always a positive side and negative side. These things affect things like boiling points and melting points, and obviously the stronger the intermolecular force, the higher these things would be. Also, in terms of dispersion forces, its strength does increase with the larger the molar mass. So larger molar mass would allow more electrons, more places for interactions to occur, and would have a stronger dispersion force than somebody that is a little less in terms of molar mass. So in comparison to sort of dispersion force versus dispersion force sort of strength, it does increase with molar mass because there's more electrons. We also talked about sort of the different states and stuff and changing from one state to the next, like melting and freezing, evaporation and condensation, and sublimation and deposition. And we talked about, again, there are a certain amount of energy required to do just some of those phase transitions as you go melting and freezing, which occurs at sort of the same temperature, to just do the transition, not change the temperature. That is the delta H of fusion that we talked about. and that is the energy required basically to change the state of a substance, but not its temperature. So that is normal sort of melting and boiling point. Evaporation and condensation also occurs at the same spot. That is the normal boiling point, and that also requires a delta H of vaporization that we talked a little bit about. And again, that happens, for example, for water at 100 degrees Celsius, at exactly 100 degrees Celsius. You do have both phases sort of always happening at once. This led us to sort of the end there where we were starting to talk about phase diagrams and phase diagrams. Phase diagrams show the different phases. So it shows the solid, the liquid, and the gas phase. And it shows the basically temperature pressure combinations that are necessary to maybe do some transitions, or what phases these things would be in depending on the temperature and pressure sort of situations. There is sort of a critical point, which is usually around here between liquid and gas. And that's the point pretty much where liquid and gas sort of fade into each other. That's where we have our supercritical fluid happening up in that corner of sort of the phase diagram. And that is something that sort of flows like a gas, but has some properties like liquid as well. They sort of intermix. You also find some lines that kind of come through. Very badly drawn one here. And there's also a point where, there's a triple point where all three phases are occurring all at once. Again, if you find yourself sort of on the line in this phase diagram, that's usually a transition point between, say, solid and liquid would be where melting would occur as well. Any questions on any of that there? All right, so then let us continue on with that phase diagram stuff here, I think. So let's see where we left off here. Oops. So here is a phase diagram for carbon dioxide. And carbon dioxide, again, this phase diagram shows our solid, which is always usually in this quadrant, our liquid, and then our gas here. And this is the critical point here. So this is the point where above it in terms of temperature and pressure, and that's where you find your critical temperature and critical pressure. Again, it sort of is a little off of this diagram, but it is sort of where, again, that sort of liquid phase sort of flows into the gas phase. So when we think about something like carbon dioxide, which is dry ice basically goes directly from solid to gas, right? Goes through sublimation, no liquid thing. And that's because normal pressure, if we look at this graph right here, normal pressure is 1 atmosphere. And if we go across that 1 atmosphere in terms of pressure, and we go from it was really cold to room temperature, like over here, the only transition that we made was going directly from solid to gas, and it went through sublimation. We did not pass the liquid part in this case. So out here would be where obviously sublimation would occur. So that is why when we have something like dry ice here under normal conditions, it does that. It does go from solid directly to gas. If we wanted to force the dry ice to go into the liquid phase, we would need to do a couple of things. One thing for sure is we would need to raise the pressure to above 5.1. So we'd have to get that pressure above 5.1. And then if we kind of take it across, it will pass through, obviously, the liquid phase in that case. Again, normal pressure is about 1 atmosphere. So you need about 5 times the pressure there or more to try to force something like dry ice into the liquid state. So that's why something like dry ice doesn't normally go through the liquid state under normal conditions, because obviously our pressure is more 1 atmosphere than very, very high pressure. Any questions on that there? In case here, this would be the triple point for carbon dioxide. So if you got it to a pressure of 5.1 and you're somewhere around that temperature, wherever that may be ish, minus 56-ish, you could have actually all 3 phases sort of happening at that point, or minus 56. All right, so let's take a look at this one here for CO2, which is what we were just looking at here, I believe. Take a second, and based on all these sort of combinations, what phases would we expect everybody to be in? So for each of those things, 20 degrees, 72.9 atmospheres, and so forth, figure out what phase or phases. Okay, let's take a look. So we'll start with the first one, which is 20 degrees Celsius, which is somewhere here-ish. and 72.9, which brings us up to here. So we should be in the liquid phase at this point. At minus 56.7, which would be here, and 5.1, which would be right there. That is the triple point. So that again is the point where the temperature pressure comes together, that we have all three phases basically occurring at once. So this would be our solid, our liquid, and our gas phase happening at that point. Any questions on that one there? Looking at 10 degrees Celsius, which is somewhere in this range, and 1 atmosphere, which is across here, puts us somewhere right about there. And once again, this is the gas phase on this side over here. And that definitely would mean we would be in a gas phase at that point. At minus 78.5, which brings us back here, and at 1 atmosphere, which puts us right about there-ish. If I could draw a bigger circle, there we go. And that actually puts us right on the line there coming through. And on that line, again, is sort of that transition between phases. So at that point, you would have both phases occurring at once. So that is the transition between solid and gas at that point. And that's basically our sublimation sort of happening. And lastly here, 50 and 80. So 50 would be past 30. And up to 80, which would be past 72. So that is that point past the critical point, which is right there, where we have our supercritical fluid, where again, it has really the properties both of liquid and gas as it sort of fades from the liquid into the gas phase in that range up there, sort of past that point of critical temperature and critical pressure. Any questions on any of those there? Okay. So you do need to obviously know what a phase diagram looks like. You need to know where you would find solid, liquid, and gas on a phase diagram. You also need to know where you would find those transitions occurring from melting, freezing, evaporation, condensation, sublimation, deposition. Remember those phases in normal conditions of 1 atmosphere. You know, if this was, say, solid to liquid, right about there, again, would be our transition that would occur from, you know, melting to freezing, coming back this way, right? At that point. Any questions on that there? Okay. All right, so let's continue talking a little bit about water a little bit here, some of the properties. So water is obviously important for life. Most of those properties is due to hydrogen bonding, which again is a really strong sort of intermolecular force. One of the sort of unusual characteristics we talked about a little bit previously as well is the density of water. It is actually less dense in the solid phase than in liquid phase, and that's a result of that hydrogen bonding happening, as we'll see on another picture here. But again, when they do sort of hydrogen bond, it ends up being in the solid state, especially because they're really strong sort of forces. When they come together, there ends up being a very, very large sort of void area, if you will, between the different water molecules. And that does sort of increase the overall volume of ice and thus drops its density down lower as well than we normally see it. So through that hydrogen bonding, we do see that. And here's again that picture of the hydrogen bonding. And I think we have a picture of water and ice here. There we go. So again, in sort of the solid state, all that open space here, creating a lot of open volume. And again, density is mass divided by volume. So increasing the volume there and lowering the density. Doesn't happen as there's a little bit more room for movement. They have a little bit more energy here in the liquid phase. So not as much volume sort of being created here. And they're able to sort of move around each other and still maintain that hydrogen bonding that occurs. And that's a very unusual sort of characteristic. Obviously, most things in their solid state are usually much more dense than in their liquid state. So a very unusual sort of property. We see that, right, if we ever, you know, put a soda can or something in the freezer to cool it down and forget about it, and come back and like the bottom is bulging out, right? And that's as the water molecules start to freeze. It needs more volume and it sort of spreads out your can and stuff like that. Now, all phases of matter, with a few exceptions, expands when heated or contracted. So liquid water below 4 degrees is bloated with ice crystals. So when warm water from 0 to 4 degrees, volume increases and results in a greater density. And this is really important for example, how water sort of freezes, if you will. Water actually freezes from the top down versus the bottom up, which is really important for like fishes and stuff like that. So what ends up happening is the warmer water kind of floats to the surface. I'm sorry, the colder water floats to the surface, and at the surface it starts to freeze, and the warmer water kind of goes down. So it actually ends up kind of freezing from the top down. It actually creates sort of an insulated layer there up on top, which is why you could cut a hole in the ice and still go ice fishing, right? The fish are still down there and everything. The entire thing is not frozen from bottom to top in most cases. And that's what we see here. Our fish here, Melvin, right, is our fish, although he does look like he's in an ice cube, but he's not. So what ends up happening here is, again, like I said, the warmer 4 degrees water, because it's more dense, sort of floats to the bottom. The cooler water kind of comes to the top, and then it starts to freeze. It actually creates a little insulator up there on top, so the rest of the water below doesn't freeze. And that's really good, obviously, for everybody living there in the bottom of the water there, so they do not freeze. Any questions on that there? All right, so we're going to just talk a little bit about solids now to finish up this chapter here. And there's a couple of different types of solids, but first off, obviously, solids are typically rigid. They're usually a lot of times packed in very, very tight to one another. There's a couple of different types of solids that we come across. One's a crystalline solid, and it's typically what we see sort of in ionic compounds. And they typically have very, very ordered arrangement of how everybody comes together in the solid state. There's amorphous solids, which don't really show long range order. So they are things like glass and organic polymers. But ionic solids and crystalline type solids, they do have really pretty ordered and repeatable sort of patterns as to how they sort of come together, as we'll talk about here in a second. So repeatable that you can essentially just take a little spot of it and basically just keep stacking it on top of each other, this little kind of cutout, and you can recreate the whole sort of pattern that occurs in solids. So let's talk a little bit about crystal lattice. A crystal lattice occurs when the solid there basically comes into the solid phase, and the crystals sort of cool down slowly, and they arrange themselves to maximize the attractive forces. So remember that when something does sort of come into the solid phase, they have less energy, but there's always going to be a way where, for example, positive sides will be near positive things and negatives will be negative things, which is the repulsive aspect of it. But they will sort of arrange themselves in a way that maximizes the attraction or the attractive forces that occur when things go into the solid phase. And that's obviously our positive and negative sides, sort of being near each other. The smallest sort of pattern of that, or repeatable sort of pattern, is what is known as a unit cell. And a unit cell is something that you could use to recreate, for example, the entire sort of three-dimensional crystal structure. So let's, for example, say we had a structure where, we have all these guys packed in together here in a solid state. And we may say to ourselves, well, if we wanted to pick a unit cell, let us just maybe say grab, this guy here. And if we did grab that guy there, what we have basically is a circle, which on the aspect maybe look like, well, that's a very good sort of unit cell, that'll allow us to sort of recreate this. But it's actually not the best type of unit cell, because although we do have, for example, the whole atom or molecule, whatever that may be, we really have no relationship of how it sits next to everybody else. So, where does the next one sort of fit into that puzzle piece, if you will? So if we choose the unit cell more like Or like maybe something like this, where we take a piece of several different sort of atoms within that structure. That would give us a unit cell that looks, something like this. As we sort of picked out all the pieces there. And now what we know is if we take this unit cell, I can basically just put another piece over here, another unit cell, which would match up like this. And I could take another unit cell and stack it up on top. And I can take another unit cell over here and stack it up this way. And now you can see we are recreating really, our overall structure here, because we not only have the actual cell, but we have the relationship of how it fits together with all its neighbors. We do lack that here, not really sure sort of where the next piece sort of fits in. So typically when we sort of grab a unit cell out, what we're looking for is something that gives the relationship of several sort of components within that solid structure that allows us to recreate, the sort of three-dimensional structure. Questions on that there? And here again is sort of an idea that unit cells are three-dimensional. They usually contain 2 or 3 layers of particles. Again, unit cells are repeated over and over to give the overall big structure of what's happening at. Again, you can probably pop that unit cell anywhere in there. Each particle in the unit cell is called a lattice point. And again, for example, here they chose this one, which gives them information about 1, 2, 3, and 4, and also the relationship of this whole atom in comparison to the other. You could actually kind of see how it all comes together. And again, you can rebuild that whole structure. And no matter where you sort of grab it out, if you grab that same unit cell, you're going to get that guy in the middle with the relationship of the 4 other ones and sort of how they sit together as well. So it's able to recreate everything. Now there's different types of unit cells. There's 7 different types of unit cells. There's cubical, tetragonal, monoclonal, and so forth. We're going to talk about just basic cubic cells here, where basically everything is 90 degrees, where the volume is the length times the width times the height, right? Or the length cube, basically, in this particular case. So we're not going to focus in on the other ones, but we're going to focus in on the different types of cubic sort of unit cells. So let's take a look at those here. So a couple of other things that we sometimes talk about here is the idea of the number of particles each one is in contact with. That's what's known as the coordination number. So for ions, it is the number of oppositely charged ions that's in contact with another. The higher the coordination number, that means the more interaction that's occurring, the stronger the attractive forces are holding that crystal together. So again, obviously a larger coordination number, there's a lot of places where everybody's interacting, which means there's a lot of attractive forces. And by the way, we're talking about a lot of times here ionic solids, which are positive and negatively charged ions, which is a very strong attractive force to begin with. So that's holding that together as well. The packing efficiency, which we're not going to talk too much about, is the percentage of which the volume of the unit cell is occupied by particles. The higher the coordination number, the more efficiently the particles are packed together. Again, got to kind of get everybody together pretty tight and dense there in the solid. So let's talk about cubic unit cells. So a couple of things about each of them. First off, all 90-degree angles at the corners of the unit cells. The length of the edges are equal. And if a unit cell is made up of a spherical particle, 1/8 of the corner is found in the cube. Half is on the face, and 1/4 is on the edge between different cubes. So, in each of the corners in a 3-dimensional sort of deal here, you're going to get 1/8 of an atom kind of separated by the guy on top to the right, to the bottom, and all that kind of stuff. Anything that's like dead on the face of it will get a half an atom sort of split right down the middle if you have something on the face of it. For us, for the most part, we're not going to do too much of a sphere type of things, but the case you need to figure out the volume of a sphere is 4/3 pi r cubed. R is the radius. For the most part, R's will center around this, where the volume of the cube is equal to the length cubed, basically, kind of like what we talked about earlier on, where we take kind of the length times the width times the height type of deal. So here are the different types of unit cells, and we're going to talk about each of these in a second individually and sort of see how they come together. There's simple cubic, and a couple important things about simple cubic is there is basically one total atom per cubic cell. So if something says it sort of crystallizes in a simple cubic arrangement, you basically have one atom. And the other important part is the edge length, as we'll talk about here, and we'll see this again in just a second, which is 2 times the radius there. And it has a coordination number of 6, which means it's able to sort of pack down about 52% of everything down into each other. The other one is and by the way, a simple cubic is sometimes referred to as SC. The next one is body-centered cubic, which is BCC, sometimes abbreviated for body-centered cubic. The difference here is there's actually 2 total atoms involved when you have body-centered. And it has a coordination number of 8, so there's basically 8 atoms in contact with each other. It has a radius of 4r divided by the square root of 3. And it can pack down 68%. So again, more coordination number, more contacts, allows everybody to kind of come in a little bit more. The last type of sort of cubic cell is going to be face-centered cubic, which has actually 4 atoms total in it. And it can pack into about 12 coordination number there, and it has a 2 times r square root of 2, although it kind of looks like it on this slide, the r is not underneath the square root, so 2r square root of 2, sometimes like that. And it can pack in a lot more at 74%. So let's take a look at each of these here a little bit closer. That wasn't the closer part. Let's take a look this way, maybe. There we go. All right, so let's take a look at cubic, the simple cubic first off. So the simple cubic basically has 1/8 of an atom. So when you kind of pull out that unit cell, what you get is basically an atom at each of the corners. And at each of the corners, you basically have 1/8 of an atom that comes out basically with this unit cell. And this are obviously 8 corners. 8 times 1/8 of an atom gives you a grand total of 1 total atom that basically occurs. So in our simple cubic, that's basically where the 1 atom resides in, 1/8 of an atom basically to add each of the corners of this 3-dimensional cube. It has coordination number of 6. And again, the important part here is that 1 atom, and that 2 times r is our our length there for our cell, 2 times the radius. And that's where we can see here, maybe a little bit easier to see or a little different. Again, in this sort of thing, if we sliced out that unit, we're going to basically take a wedge of each of these guys, which basically is 1/8 of an atom there, and each of those sort of corners that occur there. There we go. And the length, once again, is 2 times the radius that is there. And that's important to help us figure out something like the volume that's going to happen. The next one is body-centered, and body-centered, again, which is BCC. And it is 9 particles, and in this case, when we pull out the unit cell, once again, at each of the corners there, we have 1/8 of an atom, which once again, there's 8 corners, which gives us 1 total atom. And then stuck right there in the center of the 3-dimensional cell is a 1 entire whole atom total. And that is what's going to give us our total of 2 atoms total for this guy. Again, 1 entire intact atom in the middle of the cell, 1/8 of an atom on each of the corners there for a grand total of 2. And this gives us our 4 divided by 4r. I'm not sure where the r went there. So it should be 4r divided by the square root of 3 there, which will give us our edge length there. Again, because we also have the corners there, which is 6, and we also have that guy sort of in the center. Again, it comes in contact with each other about 8 times, so a little bit better packing efficiency can happen here. And as you can see here, there's our 8th wedge there on the corners, and then our 1 intact atom right there, dead in the center of that unit cell. If you pull it out, and here it shows the contact points again between the center guy and all the outside guys that are happening there, which is where our coordination number comes from. Now, the last one that you have to worry about is, like I said here, face-centered, and face-centered, which is FCC. And that, again, when we pull it out, we basically have our 1/8 of an atom here and our 8 corners, which gives us 1 atom. Now, what we have here on the face-centered is actually a really badly drawn here, but we have an atom right there on the face of each plane, which is basically dissecting this guy into a half of atom, basically slitting it right there in half. And there is 1, 2, 3, 4, 5, 6 faces to the cube. So 6 times a half gives us 3 atoms. So we have 3 atoms on the face of this cube, and we have 1 atom basically from the corners of it, and that's where we get our 4 atoms total in this case. Again, the length here is going to be 2 times r, the square root of 2. I think the square root dropped too far down there. There we go. And that would be our edge length. Here, obviously, a lot more atoms involved, a lot more guys in contact with each other, a higher coordination number, and also a higher packing efficiency. And again, this is a better way of view of it. You can see the slice there of the atom in half, basically, along with our 1/8 of an atom in each of the corners, like we saw previously. There's a better picture. There we go. All right, so what can we do with all this stuff? We can use this to help us calculate things like density, for example. So let's take a look at this one and sort of go through it here together to see how we get to something like density. So if we want to calculate the density of aluminum in grams per milliliter, or grams per cubic centimeter, which might be a better version here since this is solid. It crystallized in a face-centered cubic and has a radius of 143 picometers. So the first thing that we want to do is we want to get basically those 2 things. We want the grams and we want really the volume, which is the cubic centimeters. So this is where the face-centered comes into play. So as we talked about, face-centered basically means that it has 4 atoms. And we eventually want to get to grams here for our density. So we want to really go from atoms to grams. So atoms throws up a key member from our past here. Atoms is Avogadro's number, right? It's where we want to kind of use that in a calculation. So we would need to use Avogadro's number here to go to moles. And then we could use the molar mass to go from moles to grams. So that's the first part of the calculation here, which is really going to give us the grams part. So since it's face-centered, it has those 4 atoms, 3 on the faces and 1 on the corners. We will use Avogadro's number here, 6.022 times 10 to the 23 atoms per mole. And since this is aluminum, we will use the molar mass of aluminum from the periodic table, which is 26.98 grams per mole here. The moles will cancel, the atoms will cancel, and that's going to turn us into grams here. And if we do that, we end up with looks like 1.79 times 10 to the minus 22 grams. So if we want to calculate something like density here to get to grams, we're going to use how many atoms are on that unit cell, and obviously Avogadro's number and our molar mass to get to grams. Any questions on that there? Now, in this particular case, the next part that we need, we actually just got the grams part here. So we really need the volume part. So the volume part is going to come from the radius here. And because this is face-centered, what we know is the length here will equal 2 times the radius divided by the square root of 2. Now, you do want to watch out units here. We do want to eventually end up in really centimeters, and we're in picometers at this point. So somewhere along the way, you got to do a conversion. So personally, I'm just going to do the conversion up front. That way I don't have to worry about converting at the end. So what I'm going to convert is my radius from picometers to centimeters. So I have 143 picometers. As we can see here, pico is 10 to the minus 12. So that is going to be 1 picometer is 10 to the minus 12 meters, and there are 100 centimeters in a meter, right? Picometers cancel, meters cancel. And if I do this here, we end up with 143 minus 12 times 100. And you end up with 1.43 times 10 to the minus 8 centimeters in this case. Any questions so far on that? And again, here, you don't necessarily have to do it at this point, but might make it easier at the end to sort of do it up front. Now that I have basically my radius, which is this guy here in centimeters, I could actually calculate the length. So the length here, I might just flip a page maybe. So I have 143 minus 8. And our length here is 2r square root of 2. So putting this in would give me 2 times 1.43 times 10 to the minus 8 centimeters, square root of 2. So we'll do that. And we got root of 2 times minus 8 times 2 gives us a length of 4.04 times 10 to the minus 8 centimeters. Remember that we're looking for a volume, and in this case, right, it's grams per cubic centimeter. So we're looking for this volume. So the volume here would be the length cubed, right, which gives us centimeters times centimeters times centimeters, because each of the lengths are the same. So that would give us 4.04 times 10 to the minus 8 centimeters cubed. And if we do that there, we have a button, so that's good. I'll hit that. That gives us 6.62 times 10 to the minus 23 cubic centimeters. So we're using the appropriate length equation there for our face centered, which is 2r square root of 2. I got it into centimeters so that I would end up with cubic centimeters, which is what we're looking for in terms of our volume. And that would be our volume. And just get the number from the previous page, 179 minus 22. All right, now this was our mass, basically, right? So at this point, we now have our grams, we now have our volume, and we could calculate the density here of aluminum, which would be 1.79 times 10 to the minus 22 grams, divided by our volume, 6.62 times 10 to the minus 23 cubic centimeters. And if you do all that there, we end up with a density for aluminum here of about 2.70. That's a long way to go to get to 2.70 grams per cubic centimeter here. Any questions on any of those steps there? So this is why it's important in terms of the different unit cells that we talked about to know how many atoms, because that's going to allow you to get to kind of the grams part of it or the mass of that. And obviously how to calculate the proper length there equation, depending on the unit cell. Any questions on any of that there? All right. Do they agree? There we go. All right, so why don't you try one here? Why don't you try this? Estimate the density. We'll do the same in grams per cubic centimeter of rubidium if the crystallizes in a body-centered cubic and has an atomic radius of 247.5. And let me find RB here. RB is I think it's 8547 maybe. Okay, let's take a look, see how you're doing. So we're looking for the density again here of RB. The important part here, it does crystallize in a body-centered. So that is, again, different than what we were dealing with a second ago. So this is body-centered. Important part for you to remember is, again, it does have two atoms in that case. Again, a whole one in the center and basically an eighth there in each of the corners. So we're going to do our same sort of approach here. We could use the idea that we know there's two atoms to get us into really the grams part that we need. So we'll take our two atoms here of RB using Avogadro's number. Again, we'll convert us into moles. And using the molar mass there from the periodic table will take us from moles to grams. Which would I say? 8547, it looks like. And once again, the moles will cancel, the atoms will cancel, and that's going to give us our grams here in this unit cell of looks like 2.84 times 10 to the minus 22 grams. Any questions so far on that there? Now, because this is also body centered here, it does have a different sort of formula for the length of an edge. And in this case, it's going to be 4 times the radius divided by the square root of 3 will equal our length. We have our length, our radius given to us in picometers, which is a very common sort of unit. So just like before, I'm going to kind of do the conversion to get it into centimeters up front, so I don't have to worry about it later. So using our picometer conversion here, 1 picometer is 10 to the minus 12 meters. And once again, 100 centimeters in 1 meter in this case. So everything cancels out. We end up with 247.5 times 1 times 10 to the minus 12 times 100 here. And that's going to give us 2.48 times 10 to the minus 8. And this would now be in centimeters. So that I could eventually get to cubic centimeters, which is sort of what I'm shooting for. At this point, a reminder that this is the radius, it is not the length. So we do have to actually put it into this formula here to calculate the length. So the length here would then be 4 times the radius we just calculated in centimeters. And that's going to be divided by square root of 3. This will then give us, looks like, uh, 5.72 times 10 to the minus 8 centimeters. Once again, this is now just a length, so we got to turn that into a volume. So the volume is equal to the length cubed here, and that would give us 5.72 times 10 to the minus 8 centimeters cubed. And if I do that, there gets us 1.87 times 10 to the minus 22 cubic centimeters, which is a volume. Yeah. Any questions up to that point? Once again, just like before, we got both of our components here that we need to calculate the density. We would definitely want to make sure we're using our exponent button for sure here in these calculations. So this is going to be 2.84 times 10 to the minus 22 grams divided by 1.87 times 10 to the minus 22 cubic centimeters, which is our volume. And that will get us Looks like a 1.52 here, grams per cubic centimeter. Any questions on any of those steps there? So not too bad, again, knowing how many atoms. Definitely you want to make sure you know that for each of those three types. Simple cubic, which has 1, body centered has 2, and our face centered there has 4. And variations on this would be, obviously, if you have the density, you could go backwards and calculate something like the radius or the the length of a cell or something like that, or even the grams kind of going backwards, or how many atoms. So that's sort of a variation on that. Any questions on that calculation there, or these calculations? The one we just did. Hopefully they agree. It's good. There we go. All right. So let's finish up a little bit talking about sort of the packing here. Again, we're not gonna get too much into it, but as these guys come together, they really do try to pack themselves in as with much efficiency in the packing. And that's again why we do associate, obviously, solids with being very rigid and very dense, usually because they're able to really pack themselves in. Layer on top of layer, basically, as they kind of come into the solid form. When they do that, we're not going to get into the specifics of how each layer is packed and stuff like that. Now, ionic solids, as most of these guys are, a lot of these guys are, can be described as simple cubic or face centered, where we have negative and positive guys sort of occupying holes among them. And an ionic solid, again, coming together in this sort of way, we do get this very, very repeatable pattern where it has very long range order that happens there. And obviously they do try to keep opposite charged ions near each other, and then obviously like charged ions not near each other. And obviously these would be our negative guys as they are larger, right? These would be our positive guys, which are smaller because they lost electrons in this particular case. All right, any questions on that? So for this, like I said, you do need to know for simple cubic, body centered and face centered, how many atoms. Perhaps the formulas for calculating the lengths will be provided for you, like the 2r, the 4r squared, and all that kind of stuff. But you do need to know how many atoms each of those guys have, sort of where they are and stuff like that. Any questions on any of that stuff from this chapter here? All right, so that should wrap up chapter 9. So we will roll off to chapter 10 here. Just give me a second, I think. To chapter 10, second to last chapter. That can't be bad. This will be the last chapter that will be on our next exam on Monday. So we're talking a little bit about solutions here. And towards the end, we're talking a little bit about solubility here. And again, why certain solutions, mix together, why certain ones do not. We'll also review some of those concentration type units that we talked about earlier on when we're doing titrations. Then we'll kind of finish up this chapter talking about colligative properties, adding solute, and how it sort of affects things like boiling point, freezing point, osmotic pressure. So let's start with liquids and liquids. So when two liquids are completely soluble in one another, they are said to sometimes to be miscible, which is another way of basically saying that they are soluble. And obviously, if you have two liquids that mix, when you mix them together, they basically all just look like one phase, right? Everything mixes together. You really don't see different layers or anything like that. So if you take some ethanol and water and sort of mix them together, it would all just kind of look like one sort of solution that's in there. So in a solution, the solute-solvent interactions is the form of hydrogen bonding. So something like ethanol, which is sort of this guy here. And water, obviously, which is this guy, which is polar, this being more negative, this being positive, the hydrogen. And it's really this part of ethanol that's able to interact the same way. That's a negative, and that's a positive polar bond. So once again, they're able to do that sort of hydrogen bonding between the two. and that makes them very soluble in each other. So as we may have talked about when we were talking about intermolecular forces in the previous chapter, although this ethanol has a non-polar side, which is sort of the carbons and the hydrogen side, it does have that small little polar side that allows it to interact really well with something like water. So they do mix very, very well through that hydrogen bonding that occurs between the hydrogen, for example, and the ethanol, and the oxygen in the water. When we do mix two sort of liquids together that really don't mix and they're sort of insoluble in each other, sometimes it's referred to as being immiscible in each other. And in that situation, we will see some layering that starts to happen. You'll see the different sort of layers depending on how many liquids, I guess, you mix together there. So for example, if we took carbon tetrachloride and water together, they wouldn't mix very well, and that is because carbon tetrachloride is this guy. If you can just quickly sketch his Lewis structure, looks something like this. And when we look at this, if we think about sort of our molecular geometry that we talked about in polarity here, this is a symmetrical geometry, right? We have basically no dots on the central atom. Everything on the outside is the same. We would expect carbon tetrachloride to be a non-polar molecule. Obviously, water, as I drew over here, is a polar molecule. And that makes very trouble when they try to come together, because as we talked about with our intermolecular forces, water is going to want to use hydrogen bonding, and carbon tetrachloride is going to want to use dispersion forces. So those are two different types of intermolecular forces, which means when they come together, they're not going to really interact really well for each other. They can maybe interact through some type of dispersion force for a very short period of time, kind of a polar, non-polar interaction. But eventually what will happen is they will sort of separate out from each other, kind of like the oil and vinegar salad dressing example, right? You kind of mix it together for a short period of time, it will stay mixed, but pretty rapidly it will kind of separate out from each other. And that's sort of the same idea here. This is also why, as we talked about maybe earlier, water is not necessarily always the best sort of solvent for everything to mix things with. And it really does have to do with sort of what you're putting together. So what we would see, obviously, in this case is some layering that would occur. We'd probably see the organic guy up on top and maybe the water sort of on the bottom here. And it's really because they don't have for a long period of time a way to maintain that interaction between them. And that is what makes really things sort of soluble in each other, is they're both sort of using the same type of intermolecular force. So whatever intermolecular forces they typically would use with themselves, if somebody else comes along that uses the same type of intermolecular force, they will be able to do the same type of interaction that they can do with themselves with that other molecule, and will make them soluble in each other. When you get basically two things that come together, they're using pretty much different types of intermolecular forces. They're not going to be able to really maintain that interaction for any period of time, and they typically will be insoluble in each other, are immiscible in the case of liquids. And that brings up the idea of like dissolves like. So as I just mentioned, things that are similar in their way they use intermolecular forces are always going to be soluble in each other, and things that are not. So polar liquids and polar liquids are going to be soluble or miscible in each other. Non-polar guys and non-polar guys will also be soluble in each other, because they both will be using dispersion forces. Again, if you cross over typically polar to non-polar, you're going to run into trouble, as again, they will be using different types of those intermolecular forces. Any questions on that there? And again, that's what we kind of see here. You can kind of see some layering that's sort of occurring as these guys are immiscible in each other. So examples of things that are soluble in water, definitely ionic compounds are soluble in water. Water being polar and ions obviously breaking apart into ions. This is where we get our ion dipole interaction that occurs. And again, that's basically like our positive ion gets surrounded by the negative side of water, while our negative ion gets surrounded by the positive side of water, which would be the hydrogen. As we might have talked about previously, that is really what makes something that's a solid dissolve, like in water. And again, it disappears, as we sort of talk about but it gets surrounded by a lot of waters, and it sort of visually disappears to us. But again, it's still there. Also, even things that are non-ionic can still be soluble in water, as the example we just saw there with ethanol, although ethanol, once again, is pretty much mostly nonpolar. So this side of it is pretty much nonpolar. It does have this polar part to it here, and it's that polar part, which is the exact same bond actually you see in water, which is our negative and positive guy here, allows something like ethanol to be very soluble in water through its hydrogen bonding ability. It does start to decrease in terms of solubility, you know, if you grabbed out some other organic guys, which is what this guy is, ethanol. If you built out, for example, our carbons didn't stop here, but our carbons just kept going and going and going, along with hydrogens attached to everything there as well, you know, all the way across. So if you built out sort of this nonpolar part, really, really large, the solubility drops tremendously. So after about, you know, maybe like 5 or so carbons that are attached there, the solubility, even though it has that OH group still attached there, drops a lot. And that's because you get into a situation was sometimes referred to in organic chemistry as what they call steric hindrance, which is a fancy way of saying something's in the way, basically. So this really big part that's nonpolar kind of gets in the way of water's ability to get to that OH group, and it decreases the solubility a lot. In addition, it makes the overall molecule really, really large, which you got this really big sort of nonpolar part and really nowhere for it to interact. The way things that are soluble, say in water or other substances, is they pretty much need to go in and replace similar type of interactions with the interactions that were there. So if you think about something like water, before everybody comes in, they're all bonded together, right, through hydrogen bonding. So for something to be soluble, you kind of have to replace those similar type of bonds with somebody coming in that's going to do something very similar. So if you have these kind of small molecules like water molecules, and you try to park like a semi truck full of carbons and hydrogens in there, it's not going to fit very well. So kind of like a garage, you can put a nice car in there, right? But you know, you try to put the semi truck into the garage, maybe you get some of it in, but most of it is not going to get into the garage and stuff like that. So that's why as you start to increase that nonpolar side, the solubility does drop a lot. Sugar, although sugar is a relatively larger molecule, what sort of helps it out in terms of being soluble is the fact that it has a lot of OH groups. So everywhere there's OH groups gives water an ability to interact with it. So it sort of overcomes that ability of, you know, it's a little bit larger of a molecule, but it has a lot of OH groups sort of filtered all through it, and it gives it a place to interact really well with it. Obviously, in the case of water, in terms of solubility, you know, for the most part, water is always using hydrogen bonding. And again, if somebody has that ability that it's interacting with water to hydrogen bond, and there's not a big sort of nonpolar side to that molecule, they should be very soluble. So this is methanol, another organic guy. So this is sort of the nonpolar part, but once again has that polar part there, that OH group that allows it to hydrogen bond really well. And there's our ethanol. Hydrogen bonding. So what about oil and water? Do they mix? Well, oil is pretty much nothing but long chains of carbons and hydrogens. Yes. Where we break down these really long chains of carbons and hydrogens through a situation called fracking, down to like 8 carbons or so, like octane, like we go fill up gas and all that kind of stuff. But for the most part, oil and stuff like that is pretty much nothing but carbons and hydrogens based on electronegativity values, as we talked about with your bonding. Carbon hydrogen bonding is pretty much nonpolar. So basically you got this giant nonpolar sort of molecule that's going to try to interact with water, which obviously wants to hydrogen bond. So once again, you really don't have a way for those two to interact. First off, oil is really large molecule using dispersion forces, and water, again, wanting to hydrogen bond. So although water can sort of do a little dispersion action for a while, and that's sort of what you see, right? If you kind of put oil and water, you know, again, you'll get a little bit of mixture there for a bit, but eventually what ends up happening is the oil, right, will kind of float to the surface there, and they really will not be able to interact or maintain that interaction over a long period of time. And that actually for oil and water is more so that example of like parking the truck in the garage there. You might get a little bit of it in, but most of it's going to come out. It's just a really large molecule and no way for it to interact over a long period of time. So again, that brings up the idea of like dissolves like. These guys would not be sort of soluble in each other. Again, they're using ultimately two different forms of intermolecular forces. Our oil using dispersion forces, and once again, our water trying to use hydrogen bonding. In terms of how things interact with each other, there's also sometimes regions on molecules which are considered hydrophilic and hydrophobic. Hydrophilic is the part of the molecule that actually likes water. So it's the water loving part. It's the part that's able to interact well with, say, water. And in terms of ethanol, that definitely would be the hydrophilic part, because that is where ethanol, once again, can interact with water through that OH bond. That would be our hydrophilic. Water. This obviously would be our hydrophobic part of it. The part that really doesn't like water, again, because it has no way to interact with it. So hydrophobic is the water hitting part, and that is really the non-polar region, say in ethanol. Soap, for example, as we'll probably see here, I think maybe down the road here, also has that. And again, that is basically how soap works. Soap is just a long chain of carbons and hydrogens. I won't draw them all in, but basically, you know, everywhere there's a carbon, there's a hydrogen, basically, repeating on. And at one end, though, it does have this group here, which is a polar group here. And that's sometimes referred to as the polar head of soap. This part here, which is all carbons and hydrogens, is the nonpolar tail of soap. And as I might have mentioned earlier, that's basically how soap works. Again, it's the nonpolar part that's attracted to dirt and that type of stuff, which is typically nonpolar. So that's the part of soap that really just grabs onto all the dirt. And then it kind of arranges itself in a pretty good way where it traps the dirt on the inside. And again, sort of aligns its outside part there of soap on the outside of it. And that is then good. So when you go wash it with water at the end, the outside part of soap will interact well with water and it will take all the dirt away. And obviously you feel cleaner in that particular case. So there are a lot of molecules, especially a lot of organic molecules, for example, that do have both of these sort of sections. They have a part that's, you know, works really well with water, can interact with water. And there's also a lot of guys that are polar. So although we think of organic compounds a lot of times as being kind of nonpolar overall, which is pretty much true because the base of everything in organic chemistry is carbons and hydrogens, but there are certain ones that have parts to it, or functional parts to it, that can interact well with water. And here's an example of that. That's octane on the left here. And that is carbon tetrachloride. Octane is, as it sounds like, maybe 8 carbons in a row with hydrogens. That is definitely a non-polar molecule. Carbon tetrachloride, as we just talked about a second ago, is also non-polar. So as we can see, when they mix here, they're both using dispersion forces, so they will mix really well. Over here, we have gasoline, which is non-polar. And obviously we have water here, which is polar. So once again, he's going to use dispersion forces. He's going to use hydrogen bonding. That is a bad situation. So we do see, again, the separation out of the two layers, as opposed to over here, where, again, they're both using dispersion forces in each of these cases. Now, solubility, obviously, when one substance is a solute, dissolves in another, which is a solvent, it is said to be soluble. A reminder that when we talk about, for example, solutions, right, there are two parts to a solution, right? There is the solute, which is the smaller part. I think we talked about when we talked about molarity and all that, and the solvent, which is the larger part of this solution. So salt is soluble in water. Obviously, when one substance doesn't dissolve in another, it's been insoluble. There's obviously a limit to solubility in one substance over another. Gases are always soluble in each other. So when you have gases, like in a mixture of gases, they're soluble in each other because they are constantly flying around, which means they are constantly mixing with each other as they're flying around in the container. So constantly mixing, they're always going to be soluble in one another. Some liquids are also mutually soluble in each other. So in terms of liquids, that's sort of what we talked about before. Polar and polar are good. Non-polar and non-polar are also good as well. Molecules, again, with similar structure tend to form solutions. And again, that's the like dissolves like. So the key here is really those intermolecular interactions. And if everybody's using the same sort of intermolecular interactions, you're good to go. If they're using very different ones, not so good to go in terms of solubility. Solubility of a solute in a solvent also depends on temperature. Typically at higher temperatures, we have a larger solubility of a solid in a liquid for a couple of reasons. Again, at higher temperatures, that's going to provide more energy, right? And more energy will allow those guys to sort of break away from the solid, also allow the solvent to move around a little bit more and have a little bit more interaction that's going to happen with the solid. So for example, sometimes if you don't have if you have a solid that will not dissolve, sometimes they have you heat it up a little bit. Again, that adds the temperature and that allows a little bit more energy to do that. Lower temperature, we see a larger solubility of a gas in a liquid. And so, for example, if we had a liquid and a gas molecule at a lower temperature, he's going to be moving slower, which means he's going to stay in the liquid part for a little bit longer period of time before he exits. And obviously, the opposite would be true if you had a higher temperature with a gas and a liquid. You would expect it probably to move out of the liquid phase a lot quicker as it has a lot more energy associated with it. The solubility of gases also depends on pressure. Higher pressure, we typically have a larger solubility. And that brings us back to our friend Boyle, right? Where if the pressure goes up, the volume goes down in this case, which means if we have a really high pressure, that means we have a very small volume, most likely. And that means if I have gas molecules in that very small volume, they're going to be near each other and mixing pretty much regularly there because they don't have a lot of room to fly around in. So they're going to be constantly mixing rather than at a lower pressure where the volume may adjust. Gives everybody a lot more room to fly around. So it may take longer for them to sort of mix across each other as opposed to if you shove them all into a very small volume. Any questions on that there? So here's just some of those interactions that we've seen. Again, this is water and an ion. Again, this is the oxygen side of water here, which is the negative side, interacting with our positive ion in this case. Let's talk a little bit about ways you could sort of classify a solution. So as I mentioned, there is sort of a limit to how much solute you can dissolve at a given solvent, and it is temperature dependent. So typically, if you increase the temperature, you could get a lot more solid to dissolve. And if you decrease the temperature, a lot less solid would be soluble in, say, something like water. So what happens when we have too much solute in a solvent? We get a solution which is referred to as a saturated solution. And a saturated solution contains basically as much of the solid that will dissolve at that particular temperature. So at that particular temperature, if you hit a saturated solution, you pretty much have put in there exactly the amount of solid or solute that will dissolve. And that means at that point, if you should add any more, say, solute to it, it would not dissolve. It would just start piling up there on the bottom. So, if you take a cup of water and you add sugar, maybe from packets, right, it'll dissolve. You take the Costco size sugar and dump it into your cup of water at some point, you could stir all day. You're not going to get all that sugar to dissolve. There's just not enough water basically to handle that much solute and stuff like that. The opposite case would be what is considered an unsaturated solution. And basically an unsaturated solution is a solution that basically hasn't hit that point yet. It hasn't hit the saturation point, which means if you continue to add more solid to it, it will continue to dissolve. It's got room for it if you want to think about it that way. And it will continue to dissolve. And you could continue to add solute until you hit a saturated solution. At that point, once you hit the saturated solution, obviously no more will dissolve at that point. But before that, you have an unsaturated solution that will continue to basically dissolve our solute. Any questions on that there? All right, I think this is a good place to lay it up